So then, if you look at this question, this is given 4 substrates of the same enzyme A, and then answer those questions. And then it's given Km and K1, Kcat, and the Vmax value. Okay. Which substrate enzyme A converts into products the fastest after substrate binding? So I think the key is that you have to interpret what is being asked first. When you said a substrate, which one is the fastest to convert into product after substrate binding, that would mean that substrate bind, which one after it binds, convert into the product fastest. So what parameters would that be? Kcat, right? Because Kcat reflects how fast it is going to form the product after substrate binding. So then this question basically asking that which substrate has the highest Kcat. Okay. And then next one is the best competitive inhibitor. We just talked about that. The best one will have the lowest Km value. Okay. Which substrate is the best substrate for enzyme A? How do we know it's the best enzyme? Best substrate? Specificity constant, right? So you just calculate the Kcat over Km, whichever one that has the highest value, that should be the best substrate among the 4. Ask if there's any ambiguity. Okay? Yes. Good. Yes. Best substrate. Yes. Okay. The question is repeat what I just said on the best substrate. The one that is the best substrate should have the highest Kcat over Km value, because the specificity constant actually reflects how better or worse the substrate it is for an enzyme. So then you just calculate which one has the highest Kcat and Km, then that's the answer. Number 12, which substrate has the highest rate of part formation? Rate of part formation is V0. So asking which one has the highest V0 when substrate is 30 km. Okay. So then V0 is equals to Vmax times substrate, Km plus substrate. Okay. So now it's given that substrate concentration is 30 km. So V0 equals to Vmax times 30 km, Km plus 30 km. So that would mean that V0 equals to 30 Vmax, Km, 31 Km. Km can go up. It's 30 over 31 Vmax. Is the V0. That is 30 substrate Km. So then the substrate that has the highest rate of part formation, simply the highest V0, simply is a constant times the Vmax. So whichever substrate has the highest Vmax should give you the highest rate of part formation. This question, no student just asked that, so I'm not going to go over again. It's clear, right, this question? Number 20, does it matter if it's affinity of suicide inhibitor? The very small Ki makes sense. Okay. So it's just that I don't see how K1, K inhibit, Ki, K dissociate, and K inact can help us. I guess that this question is related to number 22 as well. Okay. 22, let's look at that. Okay. look at the question. Okay. Which of the following inhibitors acts like a competitive inhibitor the most? So Pharm actually is correct that if you have a very low big Ki, that means it can bind the enzyme active site better. So both affinity and suicide inhibitor binds in substrate enzyme active site. So then whichever one that has the lowest big Ki, that is already a good thing. Okay? Well, that is not what the question is asking, right? Let's see. The question asks, which inhibitor acts like a competitive inhibitor? Okay. So to address that question, let's look at each one of them separately. Affinity inhibitor with a very small big Ki and a very small Ki. How does that inhibitor look like? So a very small big Ki, that means the affinity inhibitor binds very well in the enzyme active site, right? And a very small Ki, what does that mean?
No covalent bond.
It does not form the covalent bond that well, right? So does it look like a competitive inhibitor? Yes, right? So A, actually, without looking at the other choice, A is the right choice, I hope. Yeah, correct. So let's look at why the other three are not. Let's make sure. Suicide inhibitor also binds the enzyme active site, got converted, right? So to look at this one, let's see, without writing too much, let's see if we conceptualize this one. Suicide inhibitor with a very small big Ki still binds very well, good affinity. And now with a very large Ki, small Ki, what does that mean?
Irreversible.
It will bind that, it will form that covalent bond very quickly, right? And then would that look like a competitive inhibition? No, it is a very good suicide inhibitor that will bind very well, kill the enzyme, not like a competitive inhibition. So the next one, suicide. Oh, great, suicide. Suicide inhibitor, very small, big Ki, still binds very well. A very small K dissociate. What does it mean? Very small.
Substrate kind of
K dissociate. What is K dissociate? Yes. So then we know that for suicide inhibitor, it needs to bind and then become fool the enzyme as a substrate. Enzyme will start catalysis, convert the suicide inhibitor into something reactive. Once it forms reactive, it will do two things. One is that it's so reactive, bind covalent bond in the enzyme active site. A second fate for that reactive species that very reactive, but leak out to the enzyme active site, lots of water around, and then form whatever product is. So only two outcome, two possibility for that reactive species. And forming the product with the water, that is defined by small K dissociate. If you have a very small K dissociate, that means that formation of that reactive species is not going to come out in the enzyme active site, right? So then, there's a good chance that it is inactivating the enzyme. So then, it will be also a pretty good suicide inhibitor. A good suicide inhibitor should have very small K dissociate. Affinity inhibitor with a very small big Ki, same as this, but then this is just the other way around. So this one is naturally is a very good affinity inhibitor. question. Which of the, yes? What is K in F? Oh, I see. K in F is the rate constant of forming the reactive species. Upon binding of the suicide inhibitor in the enzyme active site, it has to start catalysis to form the reactive species. K, small k in F, define how fast it is to form the reactive species. And then, in this case, oh, well, actually,
Isn't that supposed to be for?
good question. Is there a K? Is there a K in that in affinity inhibitor? No. So actually, yeah. So this is not right. Thank you for that out. That is, the question is going back to one question that I sort of addressed before, but let's make sure that we all understand, okay? For this question, number 13, this is referring to the alpha of reversible inhibition, okay? Alpha is always equals to 1 plus inhibitor concentration over big KI. So only this one and that one are variables. This is a constant because any inhibitor can only have one big Ki value. So the only way that the alpha can increase or decrease is to change this inhibitor concentration. Which of the following inhibitors are the best, number 22 now, which of the following inhibitors are the best choices to be considered as a drug that acts by enzyme inhibition? Okay. So, best enzyme inhibitor. So, a good enzyme inhibitor with the one that, well, let's look at all those. Competitive inhibitor with a very large Ki. That is no Ki, so this is not, one is gone. Competitive inhibitor with a very low big Ki. This is always true, always good, because you want to have a very low big Ki for any competitive inhibitor. 2 should be one of the right one. Mixed inhibitor with a very low big Ki. Would that be good? Yes, because it means it binds very well. So these 3 must be good too. Suicide inhibitor with a very large Ki association. Let's talk about that.
Not good.
So that's not good. Yeah. So then, in terms of how effective it is to inhibit an enzyme, these 2 would be good. Yes, question? Yeah. So let's, I think the question is that if you have a mixed inhibitor and an uncompetitive inhibitor, both of them have very low big Ki. Is one better than the other? In this case, probably not. Because if you look at the definition, is that even though the mixed inhibitor can bind to the enzyme and the inhibitor, the ES complex, however, in the presence of the inhibitor, it will lower the rate of part formation rate. So it will be a slight difference in terms of how they bind. So for practical purposes, you cannot really tell which one is better. They are the same. The answer is C. Is that right? I hope not. Oh. Question is on what does it mean, what are we looking at when we look at the big Ki? Okay. The big Ki always refers to how well the inhibitor binds to the enzyme. There are two parameters. Well, the small Ki, if I understand the question right, I'm not quite sure if I understand the question. The small Ki would tell us how fast it is to form the permanent covalent bond for the inactivation, and that's only for the reversible inhibitor. And the big Ki always refers to how well an inhibitor binds the enzyme active site or enzyme active site. So there's no other better way to look at that. So can we possibly move on to handout number 2? Who said yes? Half and half. Half and half though. Yeah. The comment is that how come competitive inhibitor does not have a small Ki? Small Ki only going to be present in irreversible inhibition, because a small Ki always refers to how fast it is to form the permanent covalent bond.
How do you define what competitive I might be in a reversible competitive? Like they still have the association.
Okay, so the question is, what parameter will tell us how well the competitive inhibitor binds to the free enzyme? And that parameter is the big Ki.
I understand that, but like enzyme B plus I, and there's like a double arrow, right?
Yes.
And then EI.
Yes.
And what's the
Oh, I see. The rate constant of EI formation was the rate constant that we did not talk about.